Introduction to Probability. Before we talk about probability, we need to define an experiment. An experiment is simply an activity for which the outcome is unknown. The sample space for an experiment is the set of all possible outcomes, and an event is a subset of the sample space. So for example, suppose you toss a coin into the air and observe the side facing up when it lands. What is the sample space? Now this is a very simple example, but there's only two outcomes when you toss a coin. You can either get a head or you can get a tail, right? So the experiment is simply toss a coin and observe the side facing up when it comes to rest. The sample space consists of two elements, H for heads, T for tails. Equally likely outcomes. When each outcome of an experiment is just as likely to occur as the other outcome, then we say we are working with equally likely outcomes. So in the coin toss experiment, each outcome, heads and tails, is just as likely to occur as the other, so they are equally likely outcomes. Likewise, if we roll a six-sided die and observe the number showing on the top side when it comes to rest, the possible outcomes, which are 1 through 6, are equally likely outcomes. So in our next example, suppose you roll a regular six-sided die and observe the number showing on top when the die comes to rest. Give the sample space. Now again, this is a fairly simple example. The experiment is that we are going to roll a six-sided die and observe the number facing up when it comes to rest. So I'll remind you, when you roll a six-sided die, you are going to have one of these six faces when it comes to rest. And so what we're doing, of course, is we're counting the number of spots. And so this would be 1, this would be 2, 3, 4, 5, and 6. So the sample space is the set of 1, 2, 3, 4, 5, 6. Now for the definition of probability. For an experiment with equally likely outcomes, the probability that event A occurs is the number of outcomes in A divided by the total number of outcomes. Now for probability, the symbol that we're going to use is a capital P. And then event A, we use the capital letter A, so this would be read as the probability of event A. And it's defined to be the total number of outcomes in event A divided by the overall total number of outcomes. And one rule of probability that we can see right away is that if A is an event, then the probability that A will occur is denoted P of A, and it will always satisfy the condition that the probability of event A is always a number in between 0 and 1. Now, the reason for this is very simple. The number of outcomes of A is always less than or equal to the total number of outcomes. So that means, of course, we will always get a number that is positive, because each of these numbers is positive, but it will be less than 1 because the top number here can never be larger than the bottom number. So probabilities are always going to be a number between 0 and 1. So for a simple example here, if you roll a die and observe the number showing on the top side, what is the probability of observing a 4? So first of all, we're going to write this as the probability of getting a 4. And now we just need to think, how many ways can you get a 4? Well, of course, there's only one way to get a 4 out of 6 total possibilities. And so this probability is going to be 1 divided by 6. Now, you can give a percentage if you want. This is approximately 16.7%, but I actually prefer answers to be in fraction form. But of course, many times in the real world, answers are going to be given as a percentage. In the second part of this problem, what is the probability that we get an even number? So let's think about, in what ways can we get an even number? Well, out of the numbers 1, 2, 3, 4, 5, and 6, only the numbers 2, 4, and 6 are even. So there are 3 total possible outcomes that give you an even number out of a total of 6 possible outcomes. So this probability is 1/2, and 1/2, of course, is exactly equal to 50%. And in the final one here, what is the probability of getting a number other than 4? Now, again, this is a fairly simple problem here, right? There are 5 numbers that are not a 4. So the probability of getting a number other than 4 is 5 out of 6. And 5 out of 6 is approximately equal to 83%. Another example, suppose a box contains 5 iPods, 3 of which are blue and 2 of which are red. Without looking, you reach into the box and take out an iPod. What is the probability that you get a blue iPod? So for part A, we're going to say, what's the probability of getting a blue iPod? Well, how many blue iPods do we have? We have 3, right? So there are 3 different ways you can get a blue iPod out of a total of 5 iPods. And so this is 3 divided by 5, or 60%. And for the second part, part B, what is the probability that you get a red iPod? Well, there are 2 red iPods out of a total of 5 iPods, and that is 40%. Now let's look at a slightly more interesting problem. Suppose now that 2 dice are rolled at the same time and the numbers showing are observed. And we're going to add those numbers, okay? So first of all, what is the sample space? What is the list of all the different possible ways that 2 dice can land? For this, I'm actually going to bring in a picture. And if you look at this picture here, you can see that there's all kinds of various ways that the 2 dice can land. First of all, let's assume that one die is black and the other die is white. So when I roll a 1 on the white die and a 6 on the black die, that is a different outcome than rolling a 6 on the white die and a 1 on the black die, right? Even though they both have a 6 and a 1, the dice have to land differently for this to happen than for this to happen. Now, if we're adding the numbers together, obviously these 2 outcomes produce the same sum, don't they? In fact, if you add those, you get 7. And on top of that, there are other outcomes that also give you a sum of 7, right? So in fact, there are 6 total different ways that you can get a 7. You can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. Okay? So this is a little bit more interesting because we have more than one way that certain sums can be achieved. Now, one important point that I want you to see right away is that there are 36 total possible outcomes because the first die can land 6 different ways. The second die can land 6 different ways, and 6 times 6 is 36. So the total number of different outcomes is 36. All right, let's go back to the problem. So first of all, part A, I'm going to consider that part done. We've listed all the possibilities. There are 36 total. Now, to be fair, if you were to list these, you would say your sample space consists of, and then you might give these as ordered pairs, like you could roll 1, 1, you could roll 1, 2, 1, 3, etc., all the way up to 6 and 6, okay? And that would be 36 total. Now let's focus on part B. What's the probability that the sum is equal to 7? Well, if you remember, there were 6 possible ways that you could roll a 7 out of a total of 36 possible ways that the 2 dice can land. So the probability of getting a 7 is 6 out of 36, which is equal to 1/6 or 16.7%. Now for the next one, what's the probability that the sum is equal to 12? So if we go back here, you can see the only way to get a 12 is to roll a 6 on one die and a 6 on the other die. And there's only one way to do that. And so the probability of getting a 12 is 1 out of 36. And this is about 2.7%. So not a very good chance that you roll a 12. All right, for part D, what is the probability of getting a sum that is even? Well, let's go back and think about all the different ways you can get an even. So 6 plus 6, which is 12, is of course even. 5 and 6 and 6 and 5 make 11, so that's not even. 4 and 6 make 10. 5 and 5 make 10. 6 and 4 make 10. All of those are even. 3 and 6 make 9. 4 and 5, 5 and 4, 6 and 3 all make 9, so those are not even. 2 plus 6 is 8. 3 plus 5 is 8. 4 plus 4 is 8. 5 plus 3 is 8. 6 plus 2 is 8. That should be a 2 right here. There we go. Okay. These, of course, all give us a sum of 7, so we're not interested in that. 1 plus 5 is 6. 2 plus 4 is 6. 3 plus 3 is 6. 4 plus 2 is 6. 5 plus 1 is 6. And then we're not interested in these. 1 plus 3, 2 plus 2, and 3 plus 1 are all equal to 4. And finally, 1 plus 1 is equal to 2. So all the ones that I have circled here will give an even sum. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the probability of getting a sum that is even is 18 out of 36, which is equal to 1/2, which is equal to 50%. Now, I'd like to caution you because you might think, well, of course, it's 50% chance of getting an even and 50% chance of getting an odd. But that's not always the case. It really depends on the dice involved and what you're doing with those dice after you roll them. So try not to be too presumptuous about probabilities that seem like they're very intuitive, when in fact they may not be. And for our final problem here, what is the probability that both dice show the same number when you roll them? Now, I hope this is kind of obvious, but this is going to be 6 out of 36, right? Which is equal to 1/6 or 16.7%. And this is because if the numbers are the same, that means you have to roll a 1 and a 1, or a 2 and a 2, 3 and 3, 4 and 4, 5 and 5, or 6 and 6. So you can either roll, double 1s, double 2s, double 3s, double 4s, double 5s, or double 6s. So there are 6 ways to do this out of 36. Now let's take a look at an example involving playing cards. Suppose one card is drawn from a regular deck of 52 cards. Find the probabilities associated with the following events. So first, what is the probability that you draw an ace from the deck of cards? So we need to remember that in a deck of cards, we have 4 aces out of the total 52 cards. If you reduce this fraction, you get 1/13. And this is about 7.7%. Okay, part B. What is the probability of getting a face card? So what is a face card? So you might need to remember back to our previous video where we talked about all the different cards. But face cards are jacks, queens, and kings. And there are 4 jacks, there are 4 queens, and there are 4 kings. So there are a total number of 12 face cards in a deck. So the probability of getting one of those is going to be 12 out of 52. And if you reduce this fraction, you get 3 out of 13. And 3 divided by 13, if you change that into a percentage, you get about 23%. For part C, what is the probability that your card is a heart? Well, how many hearts are there? So again, there are 52 total cards. There are an equal number of hearts, spades, clubs, and diamonds. So that means there are 13 of each of the different suits. So there are 13 hearts out of 52 total cards. This is going to be a probability of 1/4 or 25%. And the last part, what is the probability that the card is not an ace? Well, we know there are 4 aces. And so that means there are 48 non-aces, right? Because there are a total of 52 cards. So the probability of not getting an ace is going to be 48 out of 52, which is 12 out of 13. And 12 divided by 13 on a calculator, if you want to change that to a percentage, is about 92.3%. Okay. So you will be expected to know cards and dice. Those are the only 2 situations that I expect my students to know. And of course, a coin, right? A coin is very simple, heads or tails. But I wouldn't expect you to know anything else from the real world. Those are the only 2 examples that I really emphasize in my class. Now, everything we've been talking about so far has been an example of theoretical probabilities. In other words, we can find these probabilities without actually doing anything. Another type of probabilities is what we call observed probabilities. So these are probabilities that we get from observing the real world. So for example here, the chart below shows the percentage of adolescents that do not drink alcohol. So in this age group of 12 to 17-year-olds, 83% do not drink alcohol. 17% do drink alcohol or have drank alcohol. So from this, if we randomly choose a person from this age group, what is the probability that they do not drink? Well, we would expect that probability to be 83%, right? So the probability of getting a non-drinker in this age group, according to the data that we observe here, is 83%. Now, one thing to emphasize here is this is assuming that the person is randomly chosen, okay? So we have no knowledge of the person that we're getting. We're just randomly choosing somebody, and we know 83% of this group does not drink. So the probability that one person does not drink, if randomly chosen, is 83%. Okay, so this is very different from theoretical probabilities. In other words, if I were to ask you this question without giving you this pie graph here, you would have really no idea how to answer it. And finally, the following table shows the future plans for graduating class of 300 high school seniors. So out of those 300, 259 plan to go to a 4-year college, 11 plan to go to a 2-year college, 9 plan to go to a technical or vocational school, etc. So from this group, if you randomly choose a person, what is the probability that the student plans to attend a 4-year college? So probability of getting a student who plans to attend a 4-year is going to be 259 out of 300, right? So it's just the number who say they plan to attend a 4-year divided by the total number, which was 300, and that is about 86.3%. And in the second part, what is the probability that the student plans to attend a 2-year college or a technical school? So a 2-year or technical. Well, you would have to look at how many plan to attend a 2-year, which is 11, and then how many plan to attend a technical or vocational school, that's 9. So the total number here is going to be 11 plus 9 out of 300, right? Or 20 out of 300. And 20 out of 300, if you reduce that, is going to be about 1 out of 15. And if you do 1 divided by 15, you get about 6.7%. So there were 2 groups that we were considering here. That's why we had to add these numbers together. And that concludes this video lesson.